All right.
And so it's amazing. Pretty much anything you can think of.
So you thought all the movies were going to be about Six Sigma and machining stuff, huh? I said cool YouTube video to get us in the mood. What are we in the mood for today?
You turn your microphone on first.
Turning on my microphone. Thank you. See, you now get. No. Let me change those instructions, Sean. Tell me to turn off the speakers and then turn on the microphone. Go.
Turn off the speakers and then turn on your microphone.
All right, good. Now we're capturing on echo audio also. So what are you guys in the mood to learn today? Anybody? What do you want to learn today? I forget your name, but you got the hat on there.
More about lean.
More about lean? Yeah, that's too bad. You can learn more about lean today, but you'll have to learn it. I can't teach you.
Can we learn more about how to calculate speed that would call an easy way?
Wow, what a good idea. So I get some reading stuff in here. Notice I changed it from reading, or from before class to reading. You should try to read stuff before the class, but since I didn't finish publishing this until a little bit before the class, that would have been awkward for you to rush through. But I think tomorrow's is up already, and I'll work through the weekend to make sure the rest of them for the term are up there. I'll just quickly go through some of the reading here. So it says read The Art of Manufacturing, Chapter 1. It says study the CNC Quick Guide for Haas Mills, pages 1, 2, and 3. What's the difference between read and study? Yeah.
Reading is just like looking at the words and then like memorizing it.
I hope that reading is a little bit more than just looking at the words, but I think you understand. So when I say study, I mean like be able to sort of recreate that, and it's 3 pages, and one of them half the page is a picture, and the other one the whole page is a form. And then it says review CNC Quick Guide for Haas Mills, pages 4 to 24. And so read the first 3 pages and then review what the next 40 pages. Right, so you go to CNC Quick Guide here, select the one for Mills. It'll open up here, you can say read. There's actually also an app you can download to get this, and I'll get you the link to the app too. So go through the stuff about safety, and then review the rest of this out to page 44. Okay, got that. Read is the same, so do that. Lecture slides. Somebody asked yesterday if I could get you the lecture slides in a format where you could download them, not just view them. So this should work, and this should work to view them. Okay, sweet. So we got a lecture, we got an agenda. Unfortunately, I don't have 2 projectors in this room, so I can't project the agenda for you guys today. But I did print one out for me to try to stay on track. And if you have the agenda and you see that I'm falling behind track, then you need to kick me, throw something at me. Do that. All right, so you wanted to talk about calculating feed speed, depth of cut, but I forgot your name. Yuri. Okay. I had a good friend in college. His name was Yuri, but his hair was much darker. So you don't look like him. So that's not going to help me at all. All right, Yuri wants to learn more about feed speed, depth of cut. Sean has got the important job of keeping the microphones on. Julia, what did you want to learn about today? CNC machining. Okay, cool. Tom. Feeds and speeds. Okay. What are feeds and speeds? If we had to categorize them, so I'm not big on grouping things and naming things, but if we had to call feeds and speeds something, what would we call them? All right, I'll tell you, process variables. These are, and so they're variable, right? So who's ever drawn a graph? People have drawn a graph? So when we draw a graph, what do we need to draw a graph? Yes, Tim. We need axes, right? And so if we call this one y, this one x, that's pretty common, right? It's a Cartesian coordinate system. Looks like Cartesian coordinate system. All right, so if these are our axes, and we have a variable, something that we're changing, we're choosing how to change that thing, which axis do we put it on? Usually the x, right? So this is the independent variable. And so this is the dependent variable. Right? So our process variables are the independent variables. They're independent because we get to choose them. Now, what are the dependent variables in our machining experiment here? So why do we machine something? Will. We machine something to well, yeah, if it's manufacturing, we're probably creating a product because we want to sell it to somebody. But why do we machine something? Is to change the shape of it, right? So dependent variables are going to be things like shape, right? Shape, geometry, surface finish, surface roughness, and those are the kind of things that we can impact with our machining processes. So we've got shapes over here. We've got things that we get to choose over here. Let's look. All right, so and we're going to talk about machining, right? Why do we talk about machining? Because we have machine tools here that we can talk about, and you guys can go play with them in the lab, stuff like that. So machining is a material removal process. You guys can picture that, right? So it's not an additive manufacturing process, it's a subtractive manufacturing process, right? So let's look at some material removal. This would be cooler with the audio, but not that much cooler. All right, so we're removing material here, right? What are the things as we remove this material that impact our ability to remove the material? Tim?
The hardness of the material.
So we do care about the hardness of the material. And actually the hardness relative to the hardness of the tool, right? We would like the tool to at least be a little bit harder than the material. Is it possible to do machining if the tool is not harder than the material? The tool wears out really fast. It's not impossible. All right, so material, and so you said hardness, but let's just say material properties. So material properties absolutely impact our ability to do this machining operation. Let's watch it again for a second here. Let's watch what's going on as we do it. So what do we see happening in the video? Up in the back, yeah. So the tool, and so this is a milling process, right? Because the tool is in the spindle, the tool is rotating. So the rotating tool is moving in X, Y, and Z relative to the workpiece. Okay? So we have relative motion. Relative motion of the tool with the workpiece. What else do you see? Besides the fancy video effects.
It's not like cutting it all out at once and breaking it into small parts.
So it does have, and this is over a tool path. Right, and so the tool path is the direction that the tool goes and the speed that the tool is going in that direction with our relative motion here. And it's like repeated, right? If we were to draw a picture of that tool path, and so let's say we wanted to make a pocket that was circular here. We might have the tool come in the center of this pocket and spiral. Is there a trash can over there? A term this year, I did that and it went in the can. I guess I get once. If we were to have the tool come down in the center here and spiral out, what geometry could we use to define how? Now, it doesn't have to be a spiral like that, right? It could be a square pocket. And we could have the tool come in and go like this, come over, go like this, come over, go like this, come over, go like that, right? So we can do those kind of things with the tool. How would we describe that? Tim?
Radial depth of cut.
So we've got a radial depth of cut and an axial depth of cut. Does anybody remember which one is which? It's in the, do you remember? Axial is vertical. Radial is step over. Okay, I believe that. I'm not sure it's true, but I believe it. But when you do the reading, I looked it up before I wrote it in the book. So I'm pretty sure I wrote it correctly in the book. I just don't remember. It's, you ever heard the story about the reporter asked Albert Einstein how many feet were in a mile? Anybody heard that story before? Anybody guess what his response was? Why would I fill my brain with information that I could just go look up in a reference book? So why waste time memorizing stuff that you could go look up? I don't know if I'm comparing myself to Albert Einstein, but I guess I just did. I don't have the hair for it. Tool motion. All right, so we've got a radial depth of cut, an axial depth of cut. Let's call that depth of cut. In Esprit, anybody remember what they call those things in Esprit? So one of them is, well, you've got an incremental depth. And there's a step over. And there's also a total depth. What's the difference between total depth and incremental depth? Tim?
Total depth is how far in the end.
Total depth is how deep you want the feature to be. The incremental depth is how far down is the tool going to go each time it makes one of these passes. What happens if we have the tool go down too far when we make one of these passes? Anybody know? Yeah. Usually, if we have the tool go down too far, and by the end of week 3, you guys will actually be able to prove this mathematically. If the tool goes down too far, and we keep doing the same tool motion pattern that we had programmed, let's see, 3/8 end mill, mini mill, 2 deep. So we get the mini mill spindle. You guys have heard this, right? Oh, you haven't run a mini mill yet. You've run, the super mini mill. But the super mini mill's got a different spindle. The mini mills that are in Washburn 107, they're very noisy. And it's always that frequency because we always run them at 6,000 RPM because that's as fast as that spindle goes. So it's wee. That's about what it sounds like. Sometimes it slows down a little bit, so the frequency will come down. Wee! But that's about what it sounds like if you go too deep. So incremental depth is important. Step over. All right. So we've got relative motion of the tool with the workpiece. We've got depth of cut. What else do we see? And I've said it already, but none of you have said it. Yeah. Chips are flying out, right? That's actually the real cool part. I've been in front of machines where it sounds like a machine gun with the chips hitting the glass door. That's pretty cool. Although it would have been cheaper just to have a smaller workpiece, not need to do so much of that. You guys know that, there's my iPhone. So that's an aluminum body that the phone electronics sit in. You guys know that? You know it's machined on a Haas machine? Billet machined out of stock. There's a factory in China with row after row after row after row of Haas DT1s to machine those. Pretty cool. Maybe that's why I got an iPhone. Oh no, that wasn't why. Depth of cut, relative motion. What else is going on? Yeah. Oh, what causes the chips to fly out? That's the thing. We were talking about chips. What causes the chips to fly out? The spindle spinning. All the cutting's happening because of the spindle spinning. The feed rate, so the spindle speed, let's call that speed. We have speed. I actually brought both markers that didn't work with me. Need to get a little bit more arm on it. Both of the markers that didn't work I brought with me because I was afraid that the markers in this room weren't going to work. Speed. Speed. This we'll call feed. And so that is the velocity of the tool as it makes that sideways motion, is the feed rate. Speed, feed, depth of cut. Those are the three primary process variables that control machining operations, both milling and turning operations. Let's just quickly, back here, quickly just look at this on a turning operation too. So what do we see here? What direction is the speed? Oh, and so speed here, right? This could be RPM, and it could be SFM. What's RPM mean? Up in the back. Revolutions per minute, rotations per minute, yeah. So revolutions per minute. Anybody know what SFM means? Surface feet per minute. Feet per minute or revolutions per minute. How do you go from revolutions per minute to feet per minute? Go ahead. Wait, I forget your name. And I asked you like 5 times yesterday, Robert.
I believe you multiply the revolutions per minute by the circumference in feet.
Okay. Anybody know this? So you know there's formulas for this, right? Right? And you're looking for the easy way to do it instead of the formula? I have this debate with people that teach this. Many people think that you should tell the students the formula and tell them memorize the damn formula. And since I never liked memorizing anything, and since I never liked it, I've never been good at it. I don't like that method. I like to talk about understanding the concept so that you can derive the formula if you ever needed it. And so, Robert, you said we need the circumference? So we got a circle. And so circumference equals what? Pi r squared is area. Pi times diameter. or 2 pi r, right? Pi times diameter equals the circumference. And so what are the units for circumference? And usually we measure, and so this is the same whether it's a milling tool or stock in the lathe here, right? So this is a turning operation in a lathe. And so you guys can see the rotation, right? The revolutions in the lathe. What's the diameter? Tim. We normally use inches to measure the stock diameter in the lathe or the diameter of the tool, or if we're using metric system, we use millimeters. So those are the normal units that you'll encounter here. So in this operation, how do we know what the diameter is? Because there's an outside diameter of the workpiece, right? Before we start. And there's an outside diameter of the workpiece after the tool goes by, right? Which one do we use? Robert. So it really kind of depends. So Robert wants to use the diameter before. Did you want to go before the original diameter? You can use, so a good bet is to use the average. If you use the initial diameter, then you're going to get a faster or a slower surface speed. You're going to get a higher surface speed if you use the original diameter. If you use the final diameter, you're going to get a slower surface speed. And so if you're torn about which one to use, depending on why you're using that surface speed, you might want to do the worst case. So if a faster surface speed is going to be bad for you, then use the bigger one. If a slower surface speed is going to be bad for you, then use the smaller one, just to make sure you're not outside that bound. But it really is, it's changing all along that cutting edge of the tool, right? So it's a different surface speed all along the cutting edge of the tool. So pi times diameter. And units for this is then inches per revolution. Does that make sense? If it's pi times diameter, it's inches per revolution. We need to go from RPM to surface feet per minute. How do I turn inches into feet? Multiply by 12. Divide by 12. All right, let's try it. 12 inches per foot. I like that because the inches go away and the feet come up on top, right? Okay, so that's cool. Then what? I want to go from RPM to SFM. Tim. We got to multiply by RPM. Right? Now, anybody seen one of these formulas that they post online for this? What's pi divided by 12? Yeah? 12 divided by pi is about 4. So pi divided by 12 is about 1/4. Is that right? Point something. So you'll see this equation with point something up here. Or the pi gone and a 4 down here. You'll see people write the equation that way. Why do they do that? Well, because they want to do the math in their head while they're standing in front of the machine tool. That's why people have tried to simplify these formulas. And so pi divided by 4, if you're going the other way, it's 12 divided by pi. This way, it's pi divided by 12. I never try to memorize the equation because it's so easy to figure it out, right? It's how far does it go per revolution, right? And it's the same thing, right? You guys look at this in dynamics also, right? Who's taken dynamics recently? Is this the thing where the wheel and the road? Do you do this problem? What's the velocity of the point at the top of the wheel?
Oh, yeah.
Compared to the center of the wheel, compared to the bottom of the wheel? What's the velocity at the bottom of the wheel? 0. It's not moving relative to the road. Unless it's skidding. Right, okay. So feed, speed, depth of cut. Those are the primary process variables in manufacturing. How do you know what values to use? How do you know which values to use for feed speed, depth of cut? Yeah. You can look them up. Right? You look them up. You could memorize them. What else could you do if you don't look them up? You could do some manufacturing science. And experiment. Which one's cheapest? This is an easy one. It's cheaper to look them up than it is to do the experiment, right? Good. Sometimes you have to do the experiment because maybe that tool has never been used in that material. And when they give you these feeds and speeds in the charts, they're giving you ranges typically, and they're giving you a starting point. So at about this speed, and they always give you speed as feet per minute. And what are the units for feed? Anybody remember? Yeah. Inches per minute. Or what else could it be? Inches per flute. The flute being the cutting edge on the tool. So if the tool has 3 cutting edges, you got to have 3 flutes counted. If the tool has 1 cutting edge, then inches per flute equals inches per revolution. And in the lathe, it's always inches per revolution. Because in the lathe, we typically have a 1 cutting edge. All right, so that's the feed. Speed, surface feet per minute. What's units for depth of cut? What are units for depth of cut? Yep. Inches. And last, we're using the metric system, in which case inches become millimeters. And feet become meters. If you use the metric system to do this. All right, so that's cool. Feed speed, depth of cut. Is that a better understanding now? Good. Anybody else have a better understanding now? What time is it? What time does it say I'm supposed to be here? Sweet. I'm only 15 minutes behind. Everybody stand up. Turn around. I didn't say Simon Says. You sit back down. All right. What are the rest of the PVs in manufacturing, in machining? We have feed speed, depth of cut. We got the important ones. What are the rest of them? What else impacts the? So what are the dependent variables again? What are the things we want from our machining operation? Let's just quickly. What are our dependent variables? Oh, material properties. That was up here on the board, right? I just erased it, right? That's what reminded me it was up there on the board. How come I didn't say material properties was one of the important manufacturing process variables? Because it certainly impacts your ability to cut the material, right? Possibly more than all the rest of it, because you can't cut the material unless you have the right feed speed and depth of cut for the material properties. Why isn't it a manufacturing process variable? Yes, Tim.
You might not have the ability to change it. You can't.
Because the manufacturing engineer does not get to decide what the material is. The designer decides what the material is. You may get to decide what the shape of the incoming material is, but you don't get to decide the material properties that you're going to make it out of, unless you're the designer and the manufacturing person. In that case, you get to do that. All right, but that's why it wasn't on the list. Feed speed, depth of cut are on the list. What else? But what do they make? They make shape, right? They make geometry. Notice I've stopped trying. What do we make besides geometry? So geometry includes lengths and diameters and all that stuff. What do we make besides geometry with our machining processes? Anything? Do we make color? Sometimes, but not usually on purpose. It actually, with a really sharp tool and a certain tool path, you can get the light to refract off the surface in such a way that it makes a rainbow on the surface. But as soon as it gets dirty, that goes away. So what else do we make? Surface roughness or texture? That's what machining processes make. They make surfaces at locations. And surfaces have properties of roughness and texture, or roughness and is texture. Okay, so besides feed speed and depth of cut, what else is going to impact this in our manufacturing process? Start shouting them out. Besides feed speed, depth of cut, just start shouting them out. What else? Somebody. Not a process variable. Not a process variable because we don't get to control it. Tool size, tool geometry, we'll call it. Tool geometry, what else? Tool, what else? Shout them out. Usually is lubricant or coolant, we'll call that. And I guess I'll put all the letters in lube. And it's that which helps us control the friction. Friction came up. This will help us control friction. What else? That's material property. Designer picks that. What else? What's that? Tool path. Which kind of includes feed speed, depth of cut. But we'll put it up there. What else? Because there's many different paths that can get you the same geometry. What else? Machine tool. A stiffer machine will give you a different surface roughness than a less stiffer machine. What else? What else? There's a lot more. Time of day. Day of week. Temperature. In my machine shop, we ran a process once. The tool was spinning at 4,500 RPM. Same tool in the spindle spinning at 4,500 RPM for 13 hours in one process step. The spindle got longer by 1/1000th of an inch over the course of that 14 hours because of the heat generated by the constant velocity spinning. Temperatures that impact this. Because if the spindle moves, but the controller doesn't know that it has, then your tool's going to be further away from the part than you thought it was. Temperature, time of day, day of week. Let's see. Sports. Scores. You laugh. I once had to help a company build an automated measuring system because their failure rates would go through the roof the day after the Red Sox lost. Now, it wasn't the machining process that was going bad. It was, in fact, the inspection process. Because they had a guy stood at the end of the manufacturing line, and looked at the part and said, that's a good one. Put it on the rack. Looked at the part and said, it's a bad one. Throw it away. He was angry if the Red Sox lost. So more parts were bad the day after the Red Sox lost. Sports scores. So you can see that they get less and less important as we get further away from feed speed, depth of cut, right? But there are an enormous number of things that impact our ability to do this cutting. But okay, you don't want to just know about feed speed and depth of cut, right? Because why do we care? What's your actual objective as a manufacturing engineer? To make parts for your customers, right? So what you want to know is, how do I make a part? And so what I'm going to spend the rest of today on is, how do we make a part? So we got our machining process variables. Yeah, you got all this. Material movement by large chip formation. What are the PVs? Yeah, we choose the PVs. They control the whole process. Transform art to part. I actually got a better haiku than that for you guys on this topic, though. Feed speed, depth of cut. Feed speed, depth of cut. Guessing, not recommended. Carbide, explosion. It's a thing I do. All right, so who creates the art in this process of going from art to part? The designer creates the art in the process of going from art to part, right? The art is the designer's responsibility. We'll have some couple of lectures at the end of the term where we talk specifically about doing the design for manufacturability. But this is the designer's job. Frequently in manufacturing, you don't get to negotiate with the designer. You get what they gave you. And so the designer designs the part, creates the art. What does the art do? What does the art give us? What must the art give the manufacturing engineer? Mike? It's got to give us dimensions. Probably. Tim?
The material.
It's got to give us the material, probably. What else does it have to give us? What is it? What's the minimum that it has to give us? Enough information to make the part that the designer wants. Right? That's the minimum that that art has to do. And so there's standards, there's formats for how to do this that go to making sure that the manufacturer is going to understand when you're sending stuff out and outsourcing it. But it's got to give us enough information. You guys recognize this part? Everybody got one? Pretty much everybody should have one by now. How many different ways could you visualize making this part? You guys observed one way this week of making the part. But if you need this geometry, what's the first thing you have to do if you're going to go from art to part? So you've got the art, you know what the material is. What's the first thing you've got to do in coming up with your process, Tim?
Deciding which machining process.
Deciding how you're going to do it. And you've got to decide how you're going to do it before you sit down with CAM software. You can't just sit down and write code. I think it's why so much software sucks, actually. Because people that author software, they do that because they like writing code. And they study writing code because they like writing code. And they want to go write code. And so you give them the idea of the software, and what do? They sit down in front of a computer and start writing code without having designed the software first. Good software, you can always tell because it was designed first. All right, so you've got to decide the process that you're going to use. So what are our potential processes here? Yeah. You can't really, because it's not round. It's elliptical in shape. Actually, the original design, it was tapered in two directions. Tim?
You could 3D print it.
You could 3D print it. That's an option. What else? Oh, any guess on how long it would take to 3D print something like that? Yeah. Could you 3D print it out of 6061 aluminum? You could, I think you can, or you can get an aluminum alloy, maybe not 6061. All right, so you can 3D print it. Any idea how long it would take? Guess?
6 to 7 hours.
6 to 7 hours. How long does it take you guys to make a part?
5 minutes.
5 minutes. I think we had a 5-minute tack time on that operation. Tack time is one of the lean terms that you guys should look up. We had a 5-minute tack time on that operation. That means a part came off the machine every 5 minutes. So how many 3D printers would I have to have in order to get the same tack time? Ooh, maybe that's why they built machine the iPhones. Yeah. About 72 3D printers. How much do those cost each? Ish. Any guesses? Something could do that between $500,000 and $1 million. That total of the 2 machine tools that you use cost less than one of the 3D printers. So, all right. But yeah, you got to decide what process. How else could we make it besides 3D printing? Milling, right? The way we made it. But once you've decided to put it in a milling machine, what's the minimum number of times you could put this part in the machine tool and have it make all the features? Yes. You could do it in 3, but you guys did it yesterday in 2, didn't you? So I think the minimum number is 2 because you have to make features in all 6 sides of the prism. And so at one point you have to flip the part over, which is what you guys did. So if you were going to make it in 3, how would you do it? Up until A term this year, we always made this part in 3 steps. A term this year, we started making it in 2 steps. So what I might do is lay the part down, make that little V feature at the top. Then stand the part up, make the contour and the holes, then flip the part over and make the shape that we made last there, the double taper thing with the 3-axis machining operation. So to do this though, for each of those setups, right? So if we say 3 setups, before you can do the programming, you have to decide how am I going to hold the workpiece in the machine. You have to decide what the fixturing is. You have to decide what are the tools that I'm going to use. And what goes into deciding the tool? Any guesses? Ivan, if you had to pick the tool to use to make a V, how would you choose? So what criteria do you get to choose? You get to choose the material, the shape of the tool, and the diameter, right, in a milling operation? So how would you go about thinking about that? The size of the feature, right? So because this has a radius right here, right, at the bottom. So the maximum diameter tool that I can use to make that particular feature, that radius at the bottom, is the maximum diameter is twice that radius, right? Now, if I do exactly at twice that radius, when the tool gets there, it'll make a sharp turn. It'll make a V motion. It turns out with milling tools, when you make that little V motion, it hesitates for just an instant as it changes direction. It makes the tool vibrate and chatter, and you get horrible surface roughness right at that spot. So you actually like to use a tool that's a little bit smaller than that, so it's always feeding, it's always moving through that arc. So yeah, so why don't I just get like a small tool then? Tim? Takes longer and, well, it takes longer because partly it can't remove the same volume of chips, and partly because you have to use reduced cutting forces because it won't be as strong. Bigger the tool, stronger it is, rule of thumb. So you want to use the biggest tool that you can use, but not one that's too big. Now, what if you had a really small radius there at the bottom, and you couldn't negotiate with the designer, so you had to have that radius? You could get close to it with the larger tool, and then go back and then just finish it with the smaller tool. All right, so you have to figure out each part. How am I going to hold it? So what are the features that we're going to make? What are the operations that we're going to use to do that? What are our options for operations on this? Any ideas? All right, we'll table that for a later discussion. What else? Did I miss anything important here? No, I mean, you can look at the slides and the pictures. You can see that there's a lot of stuff going on, right? In this, I mean, I don't actually know how to make a flowchart, so I'm sure I didn't use flowchart symbols correctly. but there's a lot of stuff going on here, right? You've got to identify the features. So that's each individual feature on the part. You've got to identify the tool path and the processes that you're going to use to make the part. But you can't do this until you've figured out how you're going to fixture it, what tools you're going to use, what the feed speed depth of cut are. You need to select those process variables down here. So we've got our features identified. We've got our tool path created for each of those operations, for each of the features that we have to make there. Then we have to go look in the drawer and see if we own those tools. Now, if you're smarter, you will pick only to use tools that you already know you own, and you'll have a process for doing that, right? But you got to go put those tools in the machine. You've got to set the tool offsets. You guys haven't done that yet. You will next week probably. You'll start setting tool offsets and work offsets. But when you just put the tool in the machine doesn't know how long the tool is. So you have to tell the machine how long the tool is relative to the nose of the spindle. Because all it knows is where the nose of the spindle is and where the table is. So you got to set the tool offsets. You got to put the workpiece in the machine. You've got to tell the machine where the workpiece is. You set the work offsets. You have to probably pre-process the workpiece material. So those little Y blocks you guys made, you cut them out of little blocks of material that were like 3 inches by 2 inches by 3/4 or something, 2.5, 3 by 2.5 by 3/4. Well, we bought it in 12-foot long bars. So we had to go from a 12-foot long bar to the piece of stock that goes in the machine. We could buy them in the pre-cut sizes. No, I don't want to do that because we can use those 12-foot long bars to make other parts that come out of different size stock material. You have to machine the part. You have to clean up, deburr. So what are burrs? Yeah, Tim.
Like after cutting the blade will kind of chip but not completely.
Right at the edge. So if you've got a milling tool coming across the top of a part, we're right at the edge of that part. It actually doesn't cut because the strength of the material is such that the cutting force, instead of causing it to form a chip, it'll bend it over a little bit. Right at that edge, it'll bend it over, except the little bit that it bent over is razor sharp. So burrs are bad. You can do deburring operations in your program, which really just leave a smaller burr, but that's okay, because if the burr's small enough, even if it's razor sharp, it can't cut you because it can't go deep enough in to hurt you. So clean up, put your parts out, part inspection. Right, what does part inspection let us do? We're gonna have like 1-2 lectures on this later, but what's part inspection let us do? Tim?
Quality control.
It is quality control. Why do we need quality control? So we don't ship crap to the customer. Customers don't like to get crap. So don't ship it to them. Unless you know they don't know how to measure it. Oh, and I said that on camera. Okay. Thank you guys. We have class again tomorrow, right? We're going to continue this discussion tomorrow with, once we've got all that stuff programmed in the CAM software, which you're learning how to do in the lab now. Once we get all that stuff programmed in the CAM software, how does it get to the machine? And so we're gonna talk specifically about the code that the machines use, how much you have to understand that code in order to be able to successfully use it, and how you get it from the CAM software to the machine.